Now that we've covered how we can use Gauss's law to find the electric field for spherical charge distributions in the case of conductors or metal spheres, let's go over plastic spheres or insulating spheres. We'll do 3 examples. One, a solid plastic sphere with a uniform charge density. In the second case, we'll stick to uniform charge density, but obviously we'll investigate hollow spheres. And then we'll go to non-uniform charge density, in that case, back to solid sphere. Okay, so overall 3 examples in this video lesson. So strap on your seatbelts, let's get into it. First of all, what do I mean by uniform versus non-uniform charge density? Well, get used to these symbols, lambda, sigma, and rho. These all represent some form of charge density. In the case of spreading charge out across a rod, which is really only an extension of charge along a single dimension, the x-axis, then we describe a linear charge density represented by the Greek letter lambda that represents some number of coulombs per meter. We can say this rod has a total charge of Q and a length of L, so the average charge density would be Q over L. Then we could imagine taking a sheet of charge, so very thin, right? There's a length and a width and a very tiny thickness to it that's negligible. Really, we just imagine we're spreading charge out across the, there's a z-axis and a y-axis and an x-axis. So there's no distribution along the x-axis, but we have a distribution of charge across the y-z axis. So in that case, we want to consider an area charge density, here represented not by the Greek letter lambda, oops, I spell good, but by the Greek letter sigma, right? Area charge density is some number of coulombs per square meter. Lastly, we have the Greek letter rho, which represents a volume charge density in coulombs per, yeah, you guessed it, cubic meter, which is exactly what we'll be dealing with in this video lesson because our charges are 3-dimensional spheres. So if this value of rho is uniform, that's another way of saying it's constant throughout the entire volume. So imagine making a big ball of cookie dough, right? You're going to shape cookies out of it. It's this giant sphere. Well, if you've done a good job of mixing it up, then if I were to calculate the total number of chocolate chips in the whole volume of dough, it would be the same thing as if I just took a small sample. The ratio of chocolate chip to dough in the part versus the ratio of chocolate chip to dough in the whole thing would end up being the same thing. But if I didn't mix it really well, or I mixed it in some strange way, it's conceivable I could end up with most of the chocolate chips are on the outer perimeter of the dough, and I don't find as many on the interior. So that could be described by saying that the density itself is a function of the radius. Now, whether the density is proportional to r to the first power or r to the second power, that just depends on the given example we want to choose. And by the way, it doesn't have to be like this. It could be that it's more dense in the interior and less dense at the surface. In any case, we know in some examples that the volume density of charge may be uniform, but it doesn't have to be. It could be some function of the radius. Okay, so given that, let's dig in. Start with our solid plastic sphere and see if we can figure out what's the electric field at point A, somewhere in the interior of the plastic, what's the electric field at point B, and of course, what's the electric field at point C? What's the electric field at points inside, and what's the electric field at points outside? So to find the electric field at a point inside, we'll lean on Gauss's law. We make a Gaussian surface with a radius of lowercase r. Now that Gaussian surface has enclosed this charge, right? So the amount of Q in is definitely less than capital Q, which is the charge of the whole gosh darn thing. Let's start by stating Gauss's law. The integral of the dot product of electric field and area, in other words, the total flux through the Gaussian surface, should be equal to the charge inside that Gaussian surface divided by epsilon naught. I'm going to show my work very explicitly here. First of all, let's sort of picture what the electric field lines might look like. So I'm going to create just a small patch of area on the surface of my Gaussian surface, and some electric field lines are passing through it, and then I pick another little portion. The electric field passing through here is drawn of the same length as the electric field here. I think, in other words, the intensity of the electric field is the same at all points on the surface, and these little patchworks themselves are little area vectors, and no matter which one I look at, the area vector is parallel to the electric field passing through it. So those are two separate concepts, and I want to show those ideas explicitly in my math. So first of all, we can account for the fact that the angle between dA and the electric field is 0 by getting rid of the vector notation. EdA is Qn over epsilon naught. That might look like it's trivial, but that has some meaning, and that meaning is only properly expressed if you take the time to include these symbols in your diagrams. I hope you're doing that as you go through the work and rederive these equations on your own time. It's really important to go beyond just doing the math by rote and recognizing what each step of the math represents. There's always some justification for going from one step to another. As an example, pulling the e out of the integral sign. That's not a trivial matter. We can only do that if we recognize that the length of these electric field vectors is the same everywhere. Of course, now we just mean what is the total area of our chosen Gaussian surface, which is a sphere of radius lowercase r. So we get E times 4 pi lowercase r squared is equal to Qn over epsilon naught. So I know we broke it into several steps that were all rather easy to perform to evaluate the left side of this equation. Really, we need to spend some time evaluating how much charge is inside. Well, I think we can determine that in terms of a ratio, right? We're not talking lambda. We're not talking sigma. We're talking rho as a way of describing the density of charge. So if we took all of the charge Q and divided it by the entire volume of the sphere, that would be Q over 4/3 pi capital R cubed. However, there's nothing wrong with finding the density of charge inside the Gaussian surface. That would be Qn over 4/3 pi lowercase r cubed. But because it's uniform, both of these expressions have to give the same value. So if I set those equal to one another, Qn over 4/3 pi lowercase r cubed equals capital Q over 4/3 pi capital R cubed. 4/3 cancels out, pi cancels out. And the amount of charge inside is equal to all the charge multiplied by the ratio lowercase r cubed over capital R cubed. So in step 5, we make that substitution. E times 4 pi r squared is equal to 1 over epsilon naught times capital Q lowercase r cubed, capital R cubed. So we can cancel out the r squared on this side of the equation with 2 of the powers of r here. And lastly, we get our result. E is equal to 1 over 4 pi epsilon naught Q over capital R cubed. All of those represents constants. I've accounted for everything except this remaining r. Now, notice that means r to the first power, although I'm not going to write that 1. So what that tells us is a graph of electric field strength versus distance from the center of the plastic charge will not look like it did for the metal. So I'll remind you, in the case of a metal sphere, the electric field is 0 up to some point, and then from there decreases as a 1 over r squared proportionality. And of course, this is at the surface. Nope, that's not what we're going to get. Instead, we have as r goes from 0 up to the surface, meaning at points inside of the plastic versus outside of the plastic, the electric field is actually growing linearly. That's what this is telling us. A bunch of constants multiplied by r to the first. Now my guess is from there, at points outside, it will go as a 1 over r squared proportionality, but let's just apply Gauss's law and make sure that's the case. Okay, so if I want to find at a point outside, then I need to draw a bigger Gaussian surface. Let's not confuse capital R, the radius of the piece of plastic, with lowercase r, the radius of our Gaussian surface. Step 1, the integral of E dot dA equals q in over epsilon naught. Step 2, we picture the electric field lines. They're all of uniform length, and for every little patch of area dA, the angle is 0. So I guess I got to the point, I've seen this enough, I can start skipping steps. No, I'm not going to. I think it's important for the first few derivations to really show that each step has some conceptual meaning to it. So getting rid of the vector notation is conceptually independent of getting rid of, or of pulling the electric field out of the integral sign. So E times 4 pi lowercase r squared is equal to q in over, now how much q is inside? Well, no need for a ratio or any additional mathematics in this derivation. The amount of charge that's inside of this Gaussian surface is all of the charge, capital Q. So finally we get our result. The electric field is 1 over 4 pi epsilon naught, capital Q over r squared. So really, we've seen it. The electric field inside is proportional to r, whereas the electric field at points outside is proportional to 1 over r squared. And so the graph we guessed at is exactly right. By the way, you notice this is the same result we get for the electric field at points outside of a charged conductor. Yeah, once you're at points outside, it doesn't matter whether the charge is conducting or insulating. But when it comes to the electric field at points inside, definitely makes a difference. Now, if our sphere is hollowed out, then how do we find the electric field at these different points? So let's make a point 1, 2, and we make point 3 right at the surface, and then point 4 on the outside. So we might be curious what a graph looks like of electric field versus distance from the center, and we can make a few reference points. So this represents the inner radius of the plastic sphere, and then we have point B, the outer radius, and so we have 3 regions now: hollow, interior to the plastic, and then outside of the whole arrangement. So do you have any guess what the electric field is going to look like in these regions? Okay, well, let's apply Gauss's law and figure it out. First of all, let's see what the electric field would be at point 1 in the hollow region. Actually, I'm not going to go through a derivation here. I know that that Gaussian surface has a charge inside of it of 0, which is going to lead to the electric field has to equal 0 there. So if we were to try to graph this, it's all 0 up up until we get to radius of A. Okay, so now let's make a Gaussian surface. Let's get rid of the vector notation. I'll challenge you to try to explain why. In fact, you should probably add some more to this diagram and show me graphically what it meant to go from step 1 to step number 2. And you're welcome to discuss with your classmates if you have the same rationale as one another. Likewise, you should be able to show graphically why you're able to go from step 2 to step 3, which is pull the e out of the integral sign. Now, because our Gaussian surface, again, is a sphere, step number 4, e times 4 pi lowercase r squared is q in over epsilon naught. Why don't we just always start with 4? It seems to be where we end up every time. Well, because there's something to be said for coming up with the rationale for each step. It's one thing to be able to do the mathematics by rote. It's another to know the concepts behind each step of the derivation. Okay, so again, we're challenged with finding how do we determine what amount of charge lies inside of the Gaussian surface. Well, there's no charge from r equals 0 up until r equals a. And then we begin to see charge appear, and we can think of it as concentric spherical shells of charge. So this line I'm drawing is not a Gaussian surface. It represents a boundary for which we've captured just a small bit of electric charge. Now, if I want to get all the charge within my Gaussian surface, I need to go from r equals a up until I finally get to the boundary of the Gaussian surface itself. So I make another spherical shell, and another one, and another, and you get the drill. Each one of those is going to contain a little more contribution to the overall charge. And all I need to do is add it all up. Now, in the language of calculus, how do we say add it all up? Right? The amount of charge inside comes from adding up a bunch of contributions to the charge within that Gaussian surface. Now, remember that rho can be found by taking all of the charge. So if we say this hollowed out plastic sphere has a total charge of capital Q, if I divide that by all of the volume, then I guess that's really just a way of giving me the average density. This would be Q divided by, you might be tempted to say 4/3 pi, what would we say? The way I've labeled it here, I guess we'd say 4/3 pi b cubed. But remember, there isn't any charge in this region, so I need to subtract 4/3 pi a cubed, or I can just factor out the 4/3 pi. So there we go. Charge is distributed throughout a volume that's described by this formula from geometry. Okay, let's see. It's just as well to say the density is equal to any fractional amount of charge by the fractional amount of volume it takes up. So we're thinking of the fractional volume as being spherical shells. These spherical shells then have a volume of 4 pi r squared. That would like represent the, does that represent the inner surface area or the outer surface area of one of these thin spherical shells? Well, because it's so thin, that's the same thing, but that area is projected through a thickness of dr. So there we go. dV is 4 pi r squared dr. Or, in other words, if I take this mathematical expression and cross-multiply, dq is rho 4 pi r squared dr. That's exactly what I'm going to do to substitute into this formula. So to go from step 4 to step 5, we have E times 4 pi r squared is equal to 1 over epsilon naught times q in, where q in is the integral of rho 4 pi r squared dr. Now, I could pull the 4 and the pi out of the integral since they're constants, and then when I do so, they would cancel out. I can't pull the r squared out of the integral, so I can't cancel that out just yet. E times r squared equals rho over epsilon naught. And then we're just left with taking the integral of r squared dr. And here think of integration as antiderivative. So this becomes 1/3 r cubed. Oh, and remember what our limits of integration are. We have to add up all the spherical shells from the inner surface up until the edge of our Gaussian surface. So we're going from A to lowercase r, from A to lowercase r. So E times r squared is rho over 3 epsilon naught times r cubed minus a cubed. There's a few steps on this one, huh? Okay, so we have E equals 1 over 3 epsilon naught r cubed minus a cubed over r squared. Let's see, I've got the 3, the epsilon naught, r squared, r cubed, and then we still have rho. Let's go back to this expression for rho. And by the way, if it's uniform, I don't really need to make a distinction between average rho and the density of a small bit. If it's uniform, any calculation for density gives me the same thing. So I'm going to make this substitution now. Q over 4/3 pi e cubed minus a cubed. Well, at least the 3 cancels out. We can tidy this up a little bit. E equals 1 over, we've got a 4 pi epsilon naught. There's a familiar expression. We've got Q times r cubed minus a cubed over r squared times b cubed minus a cubed. And there we have it. Looks a little complicated, but let's see if it makes sense. Now, we're talking about a hollowed plastic sphere. Inner radius A, outer radius of B. But what if we want to compare that to a solid one for which we already found the result at points inside of a solid one? We found that E should be equal to 1 over 4 pi epsilon naught Q times R over capital R cubed. Well, is that what we get? Well, I guess if we imagine shrinking A until it goes to 0, that's a way of turning the hollow sphere into a solid one. And if we were to plug A equals 0 into this expression, we're going to get 1 over 4 pi epsilon naught Q times R cubed over R squared times B cubed. The R squared and 2 powers of R cancel out here, and what we're calling B in this diagram, we would almost certainly call capital R in this diagram. So yeah, it ends up giving us the same thing, which means I have a pretty good suspicion that we have derived the correct expression. Oh, now for points outside, well, gosh, you know what it comes out to? Yeah, for points outside, it's just going to be E equals 1 over 4 pi epsilon naught times all the charge divided by R squared. So we get the familiar 1 over R squared proportionality for points outside. Now, what exactly does a graph of E versus R look like given this expression? Well, I'll leave it up to you. You can use some graphing software if you want and see if you can get the shape in here. Obviously, it's not just 0, and it's not quite linear. So see if you can figure out what the shape would be for the electric field at points within the thickness of the hollowed out spherical shell. Now we're back to solid spheres, but this time the charge density we'll treat as non-uniform. So clearly it looks like there's a greater density of charge out near the edge than there is at the center. In fact, in this example, I want to suggest that the density itself is some function of the radius. And I'll make an example and say, what if it's just linearly increasing? So if I take any constant, I could say c times r to the first. In the spirit of Greek letters, I'll say rho equals alpha times r. Okay. Let me picture a thin spherical shell, not a Gaussian surface, but a thin spherical shell that takes up enough space, it captures a little bit of the overall charge. So rho is that little bit of charge within the volume of this spherical shell, which would be 4 pi r squared dr. I'm going to use that as my expression for rho as opposed to all of the charge divided by all of the volume, because in this case, that really is an average rho that's not the same thing as I would get here, right? Clearly, if I just took a sample of this, I took a little cube and pulled it out of here and said, I'm going to use this to try to analyze what's the charge density, I would think that rho would be almost 0. And if somebody else took a little core sample here, they say, oh, no, I think rho is very large. And if we take the total value over the total volume, what we'll get is an average. So let's ignore a calculation for average and stick to this expression for finding what exactly is the density at any chosen location. Okay, so let's make a Gaussian surface. Of radius lowercase r, and see if we can apply Gauss's law to find the electric field at points inside of a non-uniformly charged insulator. The integral of E dot dA is Qn over epsilon naught. We get rid of the vector notation. We pull E out of the integral, and we say that the total area is just the surface area of our spherically shaped Gaussian surface. So 3 steps in one here. The whole left side becomes E times 4 pi r squared. This is the beauty of Gauss's law. When we apply it to problems with high degrees of symmetry, what looks like a complicated mathematical expression becomes a trivial solution. Now, the amount of charge that lies inside, I'll say, can be found by summing up a bunch of little contributions to the total charge. So in this while, Gauss's law appears to be an expression with calculus built into it because we see this integral on the left side. But we don't end up performing any actual integration to evaluate the left side of the equation. And here, where we don't see any integration at all, turns out we actually have to sneak an integral into our solution there. So a little misleading, this Gauss's law, huh? So to go from 1 to 2, I did 3 steps in one. If you want to hit pause and think your way through what those 3 separate steps would be, knock yourself out. Okay, welcome back. We're all up to speed. In step 3, we have E equals 1 over r squared times 1 over 4 pi epsilon naught times the integral of rho 4 pi r squared dr, right? dq is the same thing as rho dv, and dv is 4 pi r squared dr if I'm thinking of dq as occupying little spherical shells. Now, what are my limits of integration? Well, if I want to account for all the charge that resides in my Gaussian surface, in this case, I need to integrate from r equals 0 up to the edge of my Gaussian surface. Okay, so we're going to go from 0 to lowercase r. 4 pi cancel out. And in step 4, we have E equals 1 over r squared times, now be careful, don't pull the rho out of the integral sign. It's not a constant. So times 1 over epsilon naught times the integral of, so what is rho? Well, this is just an example. This wouldn't always be the case, but fortunately we were given in this problem what we can substitute for rho. Alpha times r. And then we're still left with this r squared dr. Okay, so we can pull the alpha out of the integral sign. E equals 1 over r squared alpha over epsilon naught, and then we're left integrating r cubed dr, which is going to give us 1/4 r to the 4th. If we're evaluating from 0 to r, very easy to disregard the limits then in this case. And this r squared can cancel with 2 powers of r here, and we have E is equal to alpha over 4 epsilon naught, all multiplied by r squared. So our graph for electric field strength versus distance, well, from 0 up to the outer edge, the field is actually increasing, and not even in a linear way. But in a dramatic, or more dramatic fashion anyway, electric field is proportional to r squared. And then from there onward, it's proportional to 1 over r squared. In other words, at points outside, I'll leave it up to you to verify that all you're going to get here is E equals 1 over 4 pi epsilon naught times all the charge divided by r squared. What's the value? What's the maximum value? Well, at the surface, it's going to be 1 over 4 pi epsilon naught, all the charge divided by capital R squared. Okay, well, that's a lot to take in, huh? I encourage you to try to see if you can do all those derivations on your own without peeking. If you need to look back into the notes and give yourself a hint on 1 or 2 steps, no harm, no foul. The ability to derive these expressions based on applying concepts from one step to the next in your derivation will really put you in touch with the conceptual level understanding of Gauss's law. And as always, thanks for